So we're going to be taking notes on circular motion concepts after we go over today's warm-up. Again, you should have paper out for that. You also have an assignment that you can start today. It's not due today, but 801.2 circular motion problem set is due tomorrow. So we're going to do part of the notes today and part of the notes tomorrow over this topic. But we're going to start off with our warm-up, and our warm-up is actually related to universal law of gravitation, which is what we were talking about last week. So the warm-up question says, a force of 9.72 times 10 to the 14th newtons exists between a planet with a mass of 1.43 times 10 to the 24th kilograms and its moon, which has a mass of 8.71 times 10 to the 16th kilograms. What is the distance in kilometers between the two? So again, you should recognize questions that look like this, and hopefully immediately you're thinking, oh, I'm talking about two planets, I've got two masses, I have a force, or maybe you have a distance between them. You should automatically go to that universal law of gravitation that we talked about on Friday. So let's go ahead and do that. This is that equation, F sub g, so that's your force of gravitational attraction, equals your gravitational constant, big G, which has a value of 6.67 times 10 to the negative 11th, multiplied by your masses m1 times m2, and then divided by your distance of separation, r squared. Okay, so that's your formula. If we substitute in the values in this question, we get this. And so I have 9.72 times 10 to the 14th equals 6.67 times 10 to the negative 11th, that's my constant, multiplied by my masses, 1.43 times 10 to the 24th, times 8.71 times 10 to the 16th over r squared. So that's what I have here whenever I substitute it in. Again, I'm trying to solve for the distance between them, the r value down there in that denominator. And you had a question like this last week on Friday as well, so hopefully you figured it out then, but if not, we're going to go over it right now because some of you are getting questions like this one wrong because you are making mistakes with your algebra. Other people are having problems typing it in the calculator. Most of you, though, are getting it correct. But let's go ahead and talk about how to do this. So there is a couple different ways you can approach this for this first step. But what I went ahead and did is I took all these numbers on the right-hand side and I went ahead and multiplied them all together, because I am multiplying them in this equation. I have 6.67 times 10 to the negative 11th times this stuff. And so if I multiply all of those together, I get this. Okay, and I did round it, but I left several decimal places there. But I have 9.72 times 10 to the 14th equals 8.3077 times 10 to the 30th over r squared. And this is the point at which some of you are making mistakes. Okay, because you're just doing things that you can't do algebraically. Okay, if I were to divide both sides right now by 8.3077 times 10 to the 30th, that would not be equal to r squared. That would be equal to 1 over r squared. Okay, and so you have to make sure that you keep that in mind. When you are solving for your unknown, in this case that r, I need to isolate that variable, I need it on the top also. I don't want it in the denominator. So the next step I'm going to do is to multiply both sides by r squared so that I have this. And I'm going over these steps even though you should know it from your Algebra 1 class because I had too many people getting this wrong last week. Okay, so if I multiply both sides by r squared, I have 9.72 times 10 to the 14th times r squared. It's no longer on the bottom, equals 8.3077 times 10 to the 30th. And from here, you should not have a problem solving it. If you want to isolate that variable, now I just have to divide both sides by this 9.72 times 10 to the 14th. That would cancel it here. And then I would have to take the square root of whatever I get on this side after I divide, because this is r squared. And if you do that, this is the answer that you get, or you should get. So hopefully you've tried it. And I got 9.245 times 10 to the 7th meters. But that's not what I want to type in my open math for my warm-up, because it doesn't ask for the distance in meters. It asks specifically for me to convert it to kilometers. Guys, when you use the universal law of gravitation, you have to use meters for those distances, and you have to use kilograms for those masses. And if you're solving for one of those, that's the unit you're going to get also because of the units on that constant. So when I get my answer, it's not in kilometers, it will be in meters. So now we have to do an extra step. There are 1,000 meters in a kilometer. So I need to simply take this number that I have and divide it by 1,000, and I get this. 92,450 kilometers. Okay, that is the answer that you should have. Again, I rounded it. If you wanted to type all the digits out, it's actually 92,449.9926. Okay, but I rounded it, and it does have at least 3 significant figures, so it's going to count it right. I've got 5, in fact, but as long as you have at least 3 and you round it correctly, that's typically how this assignment's going to be scored whenever we're doing universal law of gravitation. All right, any questions about the warm-up? Okay, so please make sure that you type this in to My Open Math. And I know that you guys do have some materials on your desk that we're going to use a little bit later on in the period, but I'm going to ask for right now that you leave those alone so that we don't lose anything, because I hear some of you touching them. So leave that stuff alone, and we'll get to it later on. Let's start, though, with some notes. Okay, so we know that there is a force of gravitational attraction between any two objects with mass. So obviously there's going to be a force of gravity that exists between the Earth and the Moon. Okay, we should know that anyway because the Moon is in orbit around the Earth. Okay, but let's go ahead and take a look at the direction of that force. And I've got 4 points listed up here, and I'm going to label them one by one in my picture. So I have point A, I just added it to my diagram. What is the direction of the force of gravity acting on the Moon at point A? Which way is the Moon being pulled when it's at point A? Up, down, left, right. Those are the words I'm going to look for. Based on my diagram, which way would you say? Yeah, to the right. Okay, it would be pulled to the right. Again, it's a force of attraction between the Earth and the Moon. So the Earth's going to pull to the right on the Moon. The Moon's going to pull to the left on the Earth. Okay, they're going to pull toward each other. But I'm just looking at what the direction is on the Moon right now. So to the right. What about at this point, point B? Up, down, left, right. Up. Okay, what about at this point, point C? Left. And last one, point D. Down. Okay, you should be able to identify the direction of the force at any point that I give you in its orbit because it is a force of attraction between the Moon and the Earth. It should always be pointed toward the Earth. At each point, the force of gravity points toward Earth, which also happens to be the center of the Moon's at least mostly circular orbit. Okay, and so we're going to be talking about uniform circular motion today. Orbits are at least mostly circular. They are typically slightly elliptical, but we're going to assume for the purposes of our unit that everything is perfectly circular, unless we tell you otherwise. But yes, you have this force that is changing direction as the Moon makes its orbit around the Earth. And it's a similar idea here. Here there is a marble on a plate. And it says, if this marble moves at a constant 2 meters per second in a circle as shown, is it accelerating?
No.
Would I have acceleration
Yes.
in this example? I heard yes somewhere.
Yes.
Why do you say yes?
It's constantly down. I don't know.
It's changing direction. I know it's been a while. It's okay. It's been a while since we talked about it. We talked about it in Unit 2, but we said that you have acceleration when you have something that speeds up, slows down, or turns. And this is constantly turning because it's going in a circle. And so, yes, we absolutely do. We have acceleration here because, again, acceleration is the rate of change in velocity. My velocity is also constantly changing because velocity is a vector. It has a direction component to it. And so I have this velocity that's constantly changing even if the speed is constant. Speed's scalar. It doesn't have a direction. I can have a constant speed and still have acceleration, which is what you have when you have something moving in a circle like this marble around the plate or the Moon around the Earth. Same idea. Okay, is there a net force acting on my marble? If I have acceleration, do I need to have a net force? Yeah, that's what Newton's second law stated. It told us how to figure out the net force, or rather the acceleration from the net force. So yes, if you have a net force, you have acceleration and vice versa. Okay, so yes, there is a net force. That is what is causing this acceleration. So what is that force? What force is acting on the marble that is making it turn? It's not gravity. It was for the moon, but not for this example. Why is the marble turning?
Because the plate's moving.
Because the plate, and it's not because of that, it's because the plate is pushing against it. There's like a wall on the plate, right?
Yes.
Okay, and so the force is the wall of the plate that is pushing inward on it. So at point A, that wall of the plate would be pushing to the right. What about at point B? Up. See? Left. This should look familiar. It looks just like it did a second ago when we talked about the circular path of the moon around the earth. Okay, in each of these cases, whether we're talking about the moon going around the earth or the marble going around the plate, the forces go inward toward the center of that circular path. Okay, and if my forces go inward, my acceleration will too. What is the direction of the acceleration? Your acceleration is always in the same direction as your net force. So if my net force at point A is to the right, then my acceleration at point A is to the right. If my net force at point B is up, my acceleration is up, and so on and so forth. Okay, and we are going to add some names to this in a minute, because there are special terms that we use when we talk about objects in uniform circular motion. But let's start with a definition of uniform circular motion. This is the topic for today's notes, and it's one of the titles of the unit that we're in. We're talking not just about gravitation, but also uniform circular motion. So write this down. Uniform circular motion is motion in which an object moves along a circular path with constant speed. Okay, and because the object is turning in a circle, okay, that means that this object will have constant speed and also have acceleration. Okay, so I have constant speed with acceleration, and that's what it says. This means objects in uniform circular motion are accelerating because they turn. So we can think of both of these as being objects in uniform circular motion. We have the moon going around the earth, assuming that its orbit is perfectly circular, which we're going to make that assumption for right now. We can say this is uniform circular motion because the moon does move at a constant rate of speed in that circular path. And the same thing for this marble. We've got a constant speed as it moves around this circular path. But in both cases, we have acceleration because we have a net force pulling them inward, and so we have acceleration as well at every point along each of these circular paths. Okay, so I've already talked about the fact that there is a force acting on each of these. There's a name for that force. When you have an object in uniform circular motion, we call that force that pulls it or pushes it inward a centripetal force. Okay, so you have that term up here. Centripetal force would be what you need.
Skylar, for 1 minute?
Yes. So centripetal force is going to be the force that keeps the object in circular motion. It is directed toward the center of the circular path. If you want to make a note of this, you can as well, but that word centripetal in Latin literally means center seeking. You can see like the prefix, the centrum is what it comes from, but means center. And then the suffix, the petal, comes from another word that means to move towards, okay, or seeking. And so that's what it means, center seeking. But again, this is that force that keeps it in circular motion. Now, a centripetal force is not like a new type of force. It's not like we have tension, normal force, force of gravity, centripetal force. Centripetal force can be any force that is acting toward the center of a circular path. So in each of these examples, there's a force that is either pushing or pulling that object to keep it in a circle. What force did we say was our centripetal force for the moon around the earth? What force keeps the moon in its orbit? Gravity, right? So we have the force of gravity that the earth pulls inward on the moon, keeping it in a circle. What about the marble? We said it's from the wall of the plate. That's going to be the normal force, the support force in this case, because it's actually almost riding along the wall. but you're going to have that normal force pushing inward. So your centripetal force could be gravity, it could be normal force. In fact, it could be, and typically is, one of these four forces that I have listed down here. Okay, in fact, let's go ahead and look at these other two examples. I have a car that is going around a curve, so at least portion of a circular path. What force allows the car to move in a circle? Friction between the tires. Yeah, that's right, Drew. Friction between the tires and the roadway. Okay, now if there's not enough friction, like if you tried to do this on ice, guess what? You're not going to go in a circle. You're going to go skidding off to the side. In fact, this car's already kind of losing contact with the ground. You have to have enough friction to stay in that circular path. Okay, you have to have enough of any of these to stay in that circular path. So, but this one would be friction. What about this? This is Napoleon Dynamite playing tetherball. What force allows the tetherball to move in a circle? Tension. There's a rope, right? So there's a force of tension pulling inward. Okay, so again, it could be and typically is one of these. It could be something else, but these are the four that are most common examples of your centripetal force. Whatever the scenario is, you have to interpret it and figure out what that force is. Yes, Katie?
So you can have centripetal force without it being like a uniform circle?
Yes, you can just have a portion of a circle like the car turning, and you can still have a centripetal force during the turn. It doesn't have to go on a complete lap. Yes?
Would something like spinning have centripetal force?
If it's in place, no, not really. That's a little bit different. We don't talk a lot about rotation in here, but we do it in AP if you want to take AP Physics 1 after this. We have a whole unit on rotation. You don't have to, Austin. It's optional. Don't let your counselor tell you it's required. All right, any questions about this? All right. All right, so there is a common misconception when we look at examples of things moving in circular paths. If you look at these two, or I guess four boys, they have a motorcycle that is spinning this playground merry-go-round, which, for the record, don't do this. This looks really dangerous. But it does look like there's some kind of force that throws the guy off of the merry-go-round. There's not. Okay, there is no force that pushes objects out of their circular path. Okay, the reason that guy flies off, and he does it right here, is because of the absence of a sufficient amount of centripetal force. Okay, so if you don't have centripetal force, if you lose it or if there's not enough of it, I mentioned that with the car in contact with the road, if there's not enough friction, then you'll have your car skid off. Okay, or in this case, there was not enough normal force keeping him in. He actually went over that rail. But it's the absence of that force that causes the objects to stop traveling in a circle. Without the net centripetal force, objects in motion will continue in motion with constant velocity. That is Newton's first law of inertia. An object in motion will continue in motion with a constant speed in a straight line. That's what constant velocity means, constant speed, straight line. Okay, and we saw that with the guy that flew off. He went in a straight line, and he flew off. He fell to the ground, obviously, but that's Newton's first law. Okay, and so you have to have that force to keep that object in that circular path, but there's not some kind of force pushing outward. So we're going to look at this now. You have in front of you a plate and a marble, and we're going to use those. Let me go to the next slide for the instructions. So at your desk, you should have a plate and a marble, and there are two plates actually. One of these two plates is an entire plate. Okay, it says intact on my screen, but it's the whole plate. The other plate looks like Pac-Man because it has a pie piece missing. Okay, so you should have two of these at your desk. And it tells you in step 1 to take this whole plate, so the one that hasn't been cut, take this one, and you should have a marble, and to roll that marble around your plate to get it to go in a circular path. Okay, you can roll it once or you can, push it more than once, but you should be able to see what that looks like. Okay, I want you to then take the other one. So if you haven't done the first one yet, that's okay, do it in a second. But you're going to do the same thing with this plate, and what I want you to do is I want you to take a look at what direction the marble goes when it reaches the cutout portion of the plate. Okay, what does it do? Does Does it still go in a circular path? Which way does it go? So take a moment to try that. I'm going to give you all a minute to see what happens. And I want you to specifically look at what happens when the marble reaches the opening in the plate where the cutout is. So what happens when it leaves the plate? Does it still go in a circle? No. What does it do? Straight line. That's what I was just talking about on the previous slide. An object in motion will remain in motion in a straight line. That marble, at any given point, has a velocity that's in a straight line. It's just that there's then a force from the plate that keeps pushing it in and making it turn. Okay, if you remove that force, now you have it back in a straight line again. All right, once you're done trying that out, if you haven't tried it, please do that. But once you're done trying it out, go ahead and stack the plates back on each other and put the marble back on top so that it's all there for my next class period and we don't lose anything. Okay, but what happens when it reaches the cutout? It goes in a straight line. Okay, and it's not because there's some force that pushes it out of the circle. And let's look at another example that maybe illustrates this as well. It says if you're sitting in the back seat of a car that makes a hard left turn, you will feel pushed toward the right side of the car. Why does your body move to the right? This is even more evident like on an amusement park ride. Those ones that have like the arms and then the cars spin. You always end up smushing the person who sat on the outside. Okay, and so the question is why? Why do you feel pushed outward? And if y'all haven't been looking at my animation, there is a child that just falls out of the car in the turn. You can see it. It's about to start over. In the intersection right there. It felt pushed outward. But again, there isn't actually a force pushing outward, so why do they feel like that? And if you look, and I heard somebody just say it, but if you look at my diagram right here, my guy's in the car moving forward, the car is also moving forward. When the car starts to turn, it's due to friction between the tires and the road. So the car has that force of friction, but you don't. You're an object in motion, continuing in motion. You're not touching the road. And so you would continue moving the same direction. You were moving toward the top of my screen. You're still moving toward the top of my screen. And you will do that until something stops you. But that's going to make you feel like you're being pushed to the right. Okay, so you feel like you're being pushed to the right, but it's just your inertia. And I heard the word over there. Okay, but this is a common misconception because students often think there's some kind of force pushing outward. There's not. It's just your inertia. You're an object in motion. You will continue in motion in the same direction with the same speed until something stops you. And yes, that something is going to be the seat belt, maybe even the wall of the car, or an amusement park ride. It might be the person you're sitting next to if you end up smushed up against them in the wall of the ride. But it's the same idea. You have inertia. You want to go in a straight line. Just like that marble. You saw the marble go off in a straight line as soon as that force was removed because it also had inertia. Okay, and so it's the same idea. But there is no force pushing you outward. It's simply the result of your inertia that makes you feel like you're being pushed outward. The only force here is an inward force, okay, between the tires and the roadway that allow the car to turn. All right, so let's get some more definitions. We've already written down definitions for uniform circular motion, and hopefully you have something written down for centripetal force, but now we're going to talk about centripetal acceleration. Okay, centripetal acceleration is acceleration of an object in uniform circular motion due to the centripetal force. It will be in the same direction as the centripetal force. Again, your acceleration is always in the same direction as your net force. And so my acceleration, if my force is inward, so is my acceleration. I have them both labeled on two different diagrams here that are supposed to be illustrating the same thing. So in both cases, this guy is spinning this ball around on the end of a string, and you can see that the force at this point that I labeled is inward. Just like here, I labeled the acceleration as inward because they're in the same direction. And it's that force due to the tension in the string he's holding. Now, when we talk about centripetal, or rather uniform circular motion, my acceleration is constantly changing because the direction's changing, right? We said that it's, my force is to the right at this point, but if I picked a point at the top, it'd be down. If I picked a point on the other side of that circle, it'd be to the left here, it'd be to the right on the other side. And so because my force and my acceleration are constantly changing direction, that means I don't have a constant acceleration. I cannot use any of my kinematic equations that we learned earlier in the year. Because all of those kinematic equations that we learned that are on my board over there in black, they all assume that you have a constant acceleration. And we don't. We have an acceleration that's changing because the direction's changing. So for this unit, we have a special equation that we have to use to find centripetal acceleration. It's at the bottom of my screen. And it says that centripetal acceleration is your velocity squared divided by your radius. Okay, and you're going to use this formula to find acceleration when you have an object in uniform circular motion. Because that centripetal acceleration is the rate of change in tangential velocity. And we haven't talked about that term yet, but I will in a minute. But it's not a constant acceleration because the direction is constantly changing. So it's going to be tangential velocity squared divided by radius. We've already talked about centripetal force, so hopefully you already have a definition on your paper, but why don't you go ahead and add this formula. It's not a new one. It's just F equals ma. But if we're talking about centripetal force, we can say centripetal force equals mass times centripetal acceleration. And because we just learned a formula for centripetal acceleration, I can actually substitute that into this formula. Since centripetal acceleration is v squared over r, then by substitution, I can get this equation down here. Centripetal force is mass times v squared over r, mass times centripetal acceleration. So we have a couple of equations that we can use depending on what information we have. Okay, but we've got so far 3 of them that you can look at. But again, that centripetal force is the force that keeps the object in circular motion. It is directed toward the center of the circular path. What type of force is my centripetal force in this example? What force is pulling inward on my ball? Tension. Again, it's going to be some type of force. It's not a new type, not its own type of force, but my tension here would be my centripetal force. All right, so I had this term in tangential velocity in there. We need to know what that is too. Tangential velocity is your instantaneous linear speed of any object moving along a circular path. And it will be tangent to the circular path, which means that it is perpendicular to the radius at any given instant. I've labeled what that looks like on my diagram up here. My velocity at this point in time is perpendicular to my radius, and it is tangent to my circular path. Y'all should know what a tangent line is, I'm assuming, from your math class. Hopefully, if not, copy that down so that you know what direction it will face. Okay, the formula for your tangential velocity is just distance over time. It's not really a new formula. Okay, it's just distance over time like it was previously. However, what do we call the distance around a circle? Circumference. And circumference has the formula 2 pi r. That's distance around a circle. Divided by time around a circle once. That actually has a name too. It's called the period. So this is my formula for tangential velocity, but it's really just distance over time. It's circumference divided by period. But it will give you the same units, meters per second, that we had before. All right, by the way, which way will the ball go if the string breaks at this yellow point? Yeah, it'd go up. It'd go in the direction that that tangential velocity vector is pointing, just like your marble when it reached the edge of the plate. It went on a path that was a straight line tangent to the circular path at that point in time. If I drew my point somewhere else, well, guess what? My tangential velocity is going to point a different way, but it's always going to be at a right angle to the radius and in the direction that the thing's moving. Okay, so if I had put the point up here, like at the very top of the circle, my tangential velocity at this point would be directly to the left. Okay, because it would be, again, perpendicular to the radius at that point. And that would represent the direction that your object will move if the force is removed, whether that means the string breaks or he lets go of it, or whether you're talking about a marble on a plate where it reaches an opening. When the force is removed, you get a straight line path. That is your tangential velocity, or the direction of it will be in the direction of your tangential velocity. All right, so period was in my equation for tangential velocity, so here is your definition. The period is the time required to make one complete revolution. For math purposes, we often represent this in seconds for the examples that we're going to be dealing with. Seconds is pretty common to see because we often want our velocities, or we usually want our velocities in meters per second. So it's helpful to have our period in seconds. You can find the period if it's not given to you. Sometimes instead of saying the period is 4 seconds, they'll say the object makes 21 revolutions in 2 minutes. What's the period? Okay, and if you're trying to find the period and from information like that, you're just going to take the total amount of time and divide it by the total number of revolutions so you can figure out how much time it takes for one revolution. So for this example, I would take my total time, 2 minutes, but I would really want that in seconds, which is 120 seconds. And I would divide it by my revolutions, 21, and 120 divided by 21 would give me 5.71 seconds, and therefore it would be the period for that example. If you were doing an experiment and you wanted to find your period experimentally, you would have something moving in a circle like this in my animation over here, and you could time it, and you could say, okay, I'm going to time how long it takes to make 5 laps. And then you could divide by 5, and you'd get the time for 1 lap, or something like that. So you could find it experimentally if you were timing something moving in a circle, or if you're reading just a word problem, you might have to divide to get your period. All right, guys, for the rest of the class period today, you are working on your MyOpen Math assignment, 801.2, circular motion problem set. It is not due tonight. It is due tomorrow. Although I have given you the formulas for the math, we haven't used them yet together. So if you want to wait on the math, you can. We will go over examples of those calculations tomorrow. However, I will say this. Technically, you have already seen everything there is to see in this unit, which is why the test for this unit is so quick. You have a test on Thursday. Okay, tomorrow we will just be going over examples using the formulas that I already showed you today. And that's really it. There's not really anything else that's new. We'll review, of course, tomorrow before we add in some more stuff. But this assignment is not due till tomorrow. If you don't feel super comfortable with it, you can wait. But I would answer the concept questions today. And if you want to hold off on the math till tomorrow, that's fine. Or if you feel like you've got it, then go ahead and work through more of it. But if you have questions as you're working, please let me know.